Okay.
So thank you for your patience. So the audience is getting smaller and smaller. Only the best will stay to the end. So now, so last time I started with an infinity cohomology of hyperbolic groups because it's simple. There is cohomology in degree 1, the huge ugly stuff, and nothing later. And it turns out that for P large, the picture is somewhat the same. So for P large, depending on the group, there is cohomology in degree 1, and probably there is no cohomology in higher degrees, but this I don't know.
So I have this little question. I was not that here last time.
Yes.
So it's group cohomology, L infinity constraints.
So I'm not completely sure, but it seems to, when I say, I think of spaces, right? Rather than, not in group terms.
Okay.
So for a simplicial complex, L infinity cohomology means cochains are simply take bounded values, but they are not required to be invariant. There is no group in the picture, just cohomology of space. So when I say cohomology of group, I mean cohomology of the group as a metric space. And I claim that this doesn't depend on which geometry you put on the group. Which simply...
If it's hyperbolic.
Yes?
If it's hyperbolic, then it doesn't...
No, no. Under finiteness assumptions, if the group is type F, so it's a fundamental group of a cellular complex or a simplicial complex which is finite in all dimensions. Then I define the LP L infinity cohomology of the group as LP L infinity cohomology of the universal covering space. And I claim this doesn't depend on choices. And maybe I'll give a proof of this. But up to now, we admit this kind of general facts. So, but it's also true that the LP cohomology of a group, at least the H1, is the H1 of group with coefficient in the left LP regular representation. I naively would believe that it's the same for P equals infinity, but I just read an hour ago a statement that doesn't seem to go in this direction, so I'll be careful. For finite P, this is true. Let me write this. I've tried to hide this kind of facts up to now. Right? So G is, let's say, finitely presented. So what I call H1P of G as a space, this is isomorphic to H1 of G with values in the left regular representation, the LP regular representation. So on the way, I gave examples of explicit co-cycles, differential forms representing this LP cohomology in degree 1 for negatively curved manifolds, and explained a little bit how something similar could be done on general hyperbolic groups. So now we'll see how this interferes with a nice open problem. So which has to do with the substance geometrization conjecture. So this is this an old past now. So in old days, certain conjectures characterization of which, let's say, closed three manifolds can be made hyperbolic, and the conditions are on the fundamental group. It should be infinite. It should not split as a free product, and it should not contain a Z2. I think that was all. And this is the theorem that Perelman proved some 15 years ago. So, but nevertheless, during this very long time interval, there have been various attempts to extend certain techniques and to try alternative methods, and among them was geometric group theory. So now a fact of hyperbolic manifolds and their fundamental groups is that the ideal boundaries are topological spheres. Because of a negatively curved manifold. For a constant curve manifold, universal covering hyperbolic space with ideal boundary is this on sphere. And so this suggested the following question that Cannon probably had in mind since the early 1980s, but then this crystallized when Gromov came with this class of hyperbolic groups. And the formulation he gave is as follows. Imagine you have a hyperbolic group and whose ideal boundary is already a topological two-sphere. Can you conclude that this is a fundamental group of hyperbolic manifold, at least up to virtually up to finite index? And this, so this conjecture does not really follow from Perelman's work, because we have no three-dimensional manifolds in the picture to start with. So for a long time, people tried this as an attempt to solve a certain hyperbolization conjecture. And so now it's a bit outdated, but not quite. It remains a meaningful problem in our world. And it was especially appealing because immediately Cannon advertised it as an attempt to generalize a Riemann mapping theorem. So, in some sense, we start with a topological two-sphere with a group action, a convergence group action on it, and this equips this topological two-sphere with some kind of conformal structure. So, in Cannon's mind, the coarse conformal structure is a sequence of coverings by things, open sets, satisfying a certain number of axioms. And the conclusion is that that conformal structure has to be the standard one. So it sounds pretty much like a Riemann mapping theorem. And indeed, on his efforts to solve the problem, Cannon produced at least 2 papers which have in their title a finite Riemann mapping theorem or a combinatorial Riemann mapping theorem. 2 different theorems which have a bit of this flavor, but always putting extra assumptions on this mysterious data, which he calls a coarse conformal structure. Extra assumptions which he could not prove they had to be satisfied. So what I will describe here is pretty close from what Cannon had in mind, but with a more analytic flavor. So we start with conformal structure with a slightly different meaning. So defined as an equivalence class of metrics. And if you've attended Victor Schröder's lecture 3 weeks ago, he mentioned Möbius structures defined by cross ratios, and And once you have a space with a cross ratio satisfying Schroeder's axioms, you can speak of quasi-Möbius maps, maps which preserve the cross ratio up to a multiplicative constant. And so you can speak of quasi-Möbius structure, and that's exactly the kind of data you have under the boundary of a hyperbolic group. So you can define it in terms of cross ratio or in terms of families of metrics being pairwise Möbius equivalent, quasi-Möbius equivalent. But no canonical metric. But nevertheless, can associate some kind of Hausdorff dimension to a quasi-Möbius structure by minimizing, infimizing the Hausdorff dimensions of metrics in that class. So here, Bourdon-Pajot add the word Alfors regular. Alfors regular again means volume of balls. There is, for some measure, a measure of ball of radius r is proportional to r to some power. And so it turns out that visual metrics on the boundary of hyperbolic spaces and groups have this property. And so we can stick to this kind of metrics, which are especially pleasant. So that's Bourdon-Pajot's definition of conformal dimension. And now comes Kleiner's strategy for Cannon's conjecture. Kind of parallels Cannon's own strategy. Solve this variational problem. So prove that this infimum is achieved. So if so, then prove that the minimizers have to be very regular and be so regular that it's in fact Riemannian, provided you assume the space is a two-sphere. And then use Riemann's measurable Riemann's mapping theorem to say there is a unique conformal structure on the two-sphere, and so the group now acts conformally on the sphere, so it's a subgroup of hyperbolic isometries in your term. So there are two steps in this method. First, solve the variation problem. Second, prove regularity properties of minimizers. So the second step has been implemented in a very satisfactory way. So based on work by Keith and Laxo, who gave the first necessary conditions on minimizers, Bonk and Kleiner could prove that such minimizing metrics on two spheres have to be quasi-conformally equivalent to the round metric on the sphere. That's already some time ago. So that's a good sign. And then they put a lot of energy in studying the variation problem. And then things don't go quite as smoothly. And here is where Lp-cohomology will play a role. So we start with this initial observation that Lp-cohomology of hyperbolic groups is non-zero for P large. And so let's introduce some invariant, which is the list P for which this happens. And the calculation I did last time shows that for hyperbolic n space, this optimal P is n-1. It's least, meaning it turns out for that example that cohomology vanishes for P equals n-1. But it's non-zero for all P larger than n-1. So that's the list of a bound. So let's call this LP dimension. And I think I gave, the argument I gave in the proof of of non-vanishing of Lp-cohomology in fact proved more. It proved that Lp dimension is always less than or equal than conformal dimension. If you remember well, I started with some alpha regular metric in the gauge, quasi-Möbius equivalent to a visual metric, and blah 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 blah. And I showed non-vanishing of Lp-cohomology for all P strictly larger than this one. So I precisely proved this statement. So that's Bourdon-Pajot. And then come these regularity properties of minimizers. Precisely the result by Kiss and Laxo. If conformal dimension is achieved by some metric, then this metric is what they call Löwner. So it has plenty of rectifiable curves, enough so that you can define capacities, and that capacities satisfy the qualitative properties that we are familiar with in Euclidean plane. So then such Löwner spaces have to be connected, and so the group does not split over a finite group. And such spaces cannot have cut points, local cut points, so such groups do not split over virtually cyclic groups. And furthermore, Lp dimension and conformal dimension are equal in that case. So this is a list of regularity properties of minimizers. Upshot of a lot of work by Kies, Laxo, and others. So as a consequence, we see a potential obstruction to this variational problem. That there exist hyperbolic groups for which Lp dimension and conformal dimension differ. And the answer is yes. And I will, and these are groups which don't split over finite or virtually cyclic subgroups. So I will explain the examples. And so here we see simply Lp-cohomology as illustrating a deep problem, not solving that problem, but playing an important role anyway in that story. So let me explain the examples for which you can control both Lp-cohomology and conformal dimension. So these are amalgamations, A times C, B over C in a hyperbolic setting. So those groups are hyperbolic, and C is quasi-convex, and normal both in A and B in such a way that the resulting group G be hyperbolic. Then we also know that A and B will be quasi-convex in G, and so we will see copies of the ideal boundary of A in the ideal boundary of G. It follows that the conformal dimension of G is larger than the conformal dimension of A. So that's a good thing when with the definition of as an inf of ordinary Hausdorff dimensions. It increases under isomorphic dimensions. So we're in good shape now. So it's sufficient to take one of the groups, let's say B, to have a high conformal dimension. I didn't give any example. Take for B a hyperbolic a lattice of hyperbolic isometries. So in dimension n, so conformal dimension equals n minus 1 for n large, let's say. And now we'll play with A in order to reduce Lp dimension. And for this, we'll manage so that G have non-zero L2 cohomology. This implies, by definition, that LP dimension is less than or equal to 2. And then we are done. G has LP dimension less than 2, but conformal dimension larger than that of B, so very high, bigger than 2. So that's the example. And I don't want to have C finite or virtually cyclic, so I will take a rank 2 free subgroup. There are plenty of such quasi-convex and non-normal subgroups in harmonic groups. So now to control L2 cohomology, one uses L2 Betty numbers. So there is a Meyer-Vitoris long exact sequence in L2 cohomology, which implies a weak exact sequence in reduced L2 cohomology, which in turn implies inequalities between L2 Betty numbers. So, and the inequality is written there. So the L2 Betty numbers of G, where things just add up, as Meyer-Vitoris would suggest. That of A plus that of B minus that of C. Now let's arrange to have this positive. So we'll ignore B, whose L2 Betty number has to be 0. For the example I chose, at least. And concentrate on A and C. So let's take a C rank 2 two-degenerated free subgroup. So then for free groups, L2 Betty numbers are easy. So we know that the Euler characteristic of the free group on this N generator, it's fundamental group of a bouquet of circles with one vertex and N edges. But this is also the L2 Euler characteristic. So it's B0, 2 minus B1, 2 plus B2. Wait, stops there because here we're dealing with a one-dimensional complex. And B02 equals 0 because the group is infinite. And so we get this B1, 2 equals N minus 1. So if N equals 2, we have B1, 2 of C equals 1. Now, for A, we want a hyperbolic group with negative Euler characteristic. So, for instance, you can use, I could use a free group again. We do, right? Yeah. Wait. Yes. Why did I want to take Bourdon buildings? There is no special reason. No, I just will. Just got confused. All we want is that, is that the L2 B1 of A be non-zero and bigger than that of C, and so a free group would do. Oh yeah, I know. I don't want that the group splits.
Yeah.
It's too easy. So that's why Bourdon and Pajot use these more sophisticated examples. So these Bourdon buildings, they are made of hyperbolic polygons with an even number of sides. Yeah. Right? So this is P equals 6. Which are glued together along their sides. And Q here is the number of incident faces or chambers. And the pattern here at vertices is given by a complete bipartite graph. So let's say with Q, so the complete Q. So an alternate description of these buildings is as polygons of groups, where the face group is trivial, and the edge groups are Z not QZ, and the vertex groups are direct products of two copies of Z mod 2Z. The fundamental group of this orbital, this polygon of groups, acts on this cell complex, which turns out to be a building in the sense of Alina. A building whose apartments are copies of hyperbolic plane tessellated by right-angled pigons. They say regular pigons. So for these spaces, Bourdon has been able to compute conformal dimension exactly and find this weird formula. And the Euler characteristic is easy to compute. And so it's easy to achieve a large dimension by taking Q large, but P not too large. And nevertheless, a negative Euler characteristic, but yeah, if P is not too small.
You wanted it, what did
no,
minus the other characteristic
no.
to be larger than this?
All we want for A is that it doesn't split and it is and it has negative Euler characteristic. So I pick a small value of Q and a large value of P. So it turns out for these buildings that LP dimension and conformal dimension coincide. So you can't make both Euler characteristic negative and larger conformal dimension possible. So here are the examples of groups for which the strategy owned by Kleiner is difficult to achieve, right? But nevertheless, I'll come. Well, there have been a lot of thoughts on these examples, among others. So, so finally, this interference of Lp-cohomology with Cannon's conjecture, this relied on these L2 Bethe numbers, which are pretty convenient, of course. And basically, the connection between Lp-cohomology and the geometry of the boundary via this boundary expression of Lp-cohomology classes. I'd like to say a bit more. So the inequality between, so the liaison between Lp-cohomology and conformal dimension goes farther. So imagine, forget about the group and consider the ideal boundary only. So I said that Lp-cohomology of the group is a certain function space called Bezow space by Bourdon and Kleiner on the ideal boundary. So Lipschitz functions are there. So there are many continuous functions in that function space. So now this forms an algebra of functions, and so it's natural to ask whether this separates points of the ideal boundary or not. And Bourdon and Kleiner's theorem is that the list P for which these continuous cohomology functions separate points of the ideal boundary, this is exactly conformal dimension. So we have an LP cohomology characterization of conformal dimension. So this algebra of continuous Bezow functions on the boundary, that's something, it's a funny toy to play with, right? And this is what Bourdon has done. So you view this as a Banach algebra with the obvious norm. Take the L infinity norm of functions plus the norm coming from LP cohomology, the Bezow norm. Then this, in principle, this algebra contains all the large-scale information about the group in the following sense. So if two groups are hyperbolic and do not split over finite groups, then, and if P is large, then any Banach algebra isomorphism between the corresponding algebras AP arises from a quasi-isometry between groups.
So, but I mean, is it the crop product and cohomology?
No.
I mean, what is the product? The crop product and cohomology that makes the Banach algebra structure?
So simply the pointwise multiplication of continuous functions.
In the coefficient. Wait, because you multiply. That's weird.
So I've cheated a little bit. So I speak of one cohomology, and I realize it by functions, because I simply say that a one cohomology class, it's an equivalence class of functions up to constants and LP functions. Right? So what I mean here, I have a function of the ideal boundary, let's say continuous. I set it to continuously to the group, and then I take its differential. And now that's a one cocycle. And I take the norm of this one cocycle, the P norm, and the inf of the P norm of representative of this one cohomology classes. So the multiplicative structure here is not the natural one, it's more like a secondary multiplication.
It makes it commutative.
Yeah.
Okay. So you can ask about the Gelfand spectrum.
That's exactly the point. So the algebra here contains only continuous functions. So the Gelfand spectrum is the boundary as a topological space plus some extra structure as expressed by this theorem. Right? In principle, everything we can want to say geometric about the group should be expressible in terms of that algebra, except that it's completely eludes us. Even
how these algebras look like, right? What you can tell me?
So in the case, I give the example of hyperbolic plane where we can take P equals 2, let's say, and then the functions there belong to the hyperbolic space H1 half. Functions with a half derivative in L2. So this algebra is made of continuous functions, and the norm takes into account the H1 half norm
So isn't the
I don't know what.
isn't the Hilbert transformation preserved in H1?
Yes.
So there is a complex structure in this case.
Yes, that's true. That's true. And it exactly corresponds to the following. If you have a function on the boundary, you extend it to a harmonic function inside and take its differential, it's a harmonic one form, take this hot star of it. It's again a harmonic one form, the 2, so it's again closed. And it's again, so the H1, 2 in 2 dimensions has the hot star, which works as a complex structure on the space H1, 2. And this is what we, and this complex structure coming from pointwise from the hot star translates in boundary terms into the Hilbert transform, which takes a function and produces its harmonic conjugate, the imaginary part of the holomorphic function that the given function is a real part of. That's right. So this happens in all even dimensions for real hyperbolic spaces. In all odd dimensions. But in odd, even for all even dimensional real hyperbolic spaces, the middle dimensional Lp-cohomology is naturally a complex space. No, not in all events. It's 2, 6, 10. It's a complex structure, and in 4, 8, it's a paracomplex structure. It's split into two real subspaces. Excuse me. So, right. So this theorem is some kind of a challenge. Which familiar geometric properties are expressible in algebraic terms? It seems to me, I don't know. I don't know. It's really invisible yet. So now there was.
So you were saying the Gelfand spectrum is identified with the boundary.
Yes.
But presumably this is not a C-star norm, and therefore the algebra itself is not just the algebra of
continuous functions. It's a sub-algebra.
More mysterious.
Yeah. So the drawback of this algebra A is that it consists of, to define it, we require the ideal boundary and this boundary extension of functions with gradient in LP and so on. Whereas, as we'll see later on, Lp-cohomology is natural under classes of transformations like coarse embeddings, which do not extend to the ideal boundary in the hyperbolic setting. And so it would be worthwhile understanding the whole H1P as an algebra and understand its Gelfand spectrum. So that's something rather ugly. Spectrum Corona would be better adapted than. So it's very large. So due to the fact that you have not discontinuous functions there, and up to now I've been unable to make use of the spectrum of that space. So here I simply made bounded functions in that space. So this then sounds more like L infinity, and the spectrum of L infinity is not so funny to handle. But that's something I tried. Now to complete with one aspect or two aspects of this theory initiated by Klein. So he's been successful in subclasses, in particular with Coxeter groups. So for Coxeter groups, Kleiner and Bourdon are able to say exactly when the variational problem of minimizing outer dimensions of matrix in the gauge has a solution or not. And when it does not, it means that the space has a non-trivial LP partition or LP foliation. So what is this? So if this algebra LP does not separate points, and it means that it defines a partition of space. And this partition indeed depends on P. And the full description of these partitions when as P varies can be found for Coxeter groups. That's pretty interesting because it provides a rather rich picture. So, especially for P varying between LP dimension and conformal dimension. What else? I'd like to say a word of the generic behavior of hyperbolic groups from this point of view. So fortunately, someone has sorted this out. So let me recall the Kromow's density model. So you fix a number of generators, a finite generating set S, and formally add the S inverse. And now, for a large integer L, you have plenty, a large number, capital N, of words, of reduced words of length N, or unreduced words in unreduced words in this alphabet. And now the randomness comes from picking a fraction of these words at random, independently. There can be repetitions, we don't care. And the number we take is n to the d, where d is some number between 0 and 1, which we will call a density. So this produces a group presentation, and we're interested in the behavior of these groups when L tends to infinity with high probability. That is, with probability tending to 1 as L tends to infinity. And here are a few results, classical now. So Gromov showed that if d is strictly less than a half, the resulting group is infinite and hyperbolic. Zouk proved that for density bigger than 1/3, the group has a Cauchy's property T, but for density less than 1/5, this is not the case. That's a theorem by Olivier and Wise. Now we're in the world of small cancellation in the classical sense. And if these densities less than 1/6, in fact, these are cubable groups. They act geometrically on cube, K0 cube complexes. So this is quite already an impressive list of results. And then John McKay comes with an estimate on conformal dimensions of such groups. So it's easy to determine the Euler characteristic, which is 1 minus twice the number of elements of S plus the number of words n to the d. So it's very large, it's like n to the d. So the log of it is d times log n, and which is proportional to L, the length of letters. And so we see that conformal dimension is proportional to log of the Euler characteristic, and with density arising here as a coefficient. So this means it's not an asymptotic. It's merely between two constants, which does not depend on D. So it's significant, especially when d tends to 0. Right? And this happens for low densities. So this is striking. So that one is able to put one's hands on the conformal dimension of such difficult groups. So for the lower bound, it's kind of classical. It amounts to studying natural Cayley polyhedron and finding some subsets which are kind of products inside that polyhedron. And the upper bound relies on Bourdon's and Kleiner's estimates on LP dimension, especially the separating LP dimension. And there's the theorem that this number coincides with conformal dimension. It's a bit unexpected that Lp-cohomology is used there again.
I think they also improved Olivier Weiss with Piotr Kropicki. They have 5 over 24. John McKay and McKay and Kropicki.
They improved
Instead of 1/5, they have 5 over 24.
I was not aware of this.
5 over 24.
Ah.
They constructed an action on a space with very targets.
So less than a reason.
Well, the interesting thing is that maybe that action is even proper, so it might be even
So
not that form.
the point here, the statement here that Olivier and Weiss were pursuing is to have a proper action. They wanted to have a Hagerup property, a immutability, and they could not quite achieve it. So, but at least they obtained something that contradicts Cashton's property. It may very well be that the limit for Hagerup property is somewhere between 5/24.
And then for some reason, actually, they say it's 1/4.
Yes.
I mean,
As a conjecture,
I
1/4.
Yeah.
Why not?
Maybe
It's the obvious
John can
thing.
explain. Maybe they have some reason to believe it. So. Yeah.
Exactly, that's a figure which is missing in this table. That's right. Okay, so next, that's all for that subject. It was a bit fast, maybe. But again, it's a question where Lp-cohomology plays some role in a kind of intricate manner. So if you're in good shape, we can start with the next point, and with locally compact, non-discrete groups. So who cares about such groups? Well, we have a Lie groups there. And we have their p-adic analogues, so which are hyperbolic. So what does hyperbolic mean? So if you pick a compact generating set for a group, such exists for Lie groups, then you can define a word metric. And this word metric, in the Lie case, will be quasi-isometric to a left-invariant Riemannian metric. And so there is a well-defined geometry up to quasi-isometry on compactly generated groups. So one can speak of hyperbolicity. So the known examples are rank 1 Lie groups, isometric groups of real hyperbolic space, and its cousins, the complex quaternionic and octonionic hyperbolic planes and spaces. So these are the rank 1 Lie groups, single Lie groups. And in the kinetic setting, the rank 1, also there is notion of rank 1, and these turn out to act geometrically on trees. So they are hyperbolic as well. So this is what I will call the rank-one type groups, Lie groups, simply for short today. Now, let me give another family of examples. Heinze groups. So, it turns out that hyperbolic space is not a single child. He belongs to a family with many brethren. So, imagine first with hyperbolic space fix a point at infinity and consider the subgroup of isometries that fits that point. Then you still have a lot of symmetry there, but you can find an even smaller subgroup which acts simply transitively on hyperbolic space. So this contains parabolic translations that preserve these horospheres, and also one loxodromic translation that maps horosphere to smaller horosphere. And so if this is n-dimensional, then the group is again n-dimensional. So it's a solvable group, since it's an extension of a nilpotent group of parabolic translation by R. And now it's a semi-direct product where R acts on N by some one parameter group of automorphisms, and here these are the dilations. So in a real hyperbolic space, N is a billion, and the action is by homocities. There is an analog for complex hyperbolic space where N will be Heisenberg group with its ordinary dilations. So you see here the parameter is a one parameter group of automorphism generated by a dilation, by a derivation. And it turns out that the condition for such a group to admit a left invariant metric of negative curvature is understood. So it's clearly an open condition. So if it works for the traditional derivation with matrix which is identity, it also works for small perturbations. And so real hyperbolic space can be obviously deformed in the family of homogeneous Riemannian manifold of negative curvature. But it turns out that the condition for such a semi-direct product to bear a negative curvature is simply that this be contracting, that is, that the real parts of eigenvalues of alpha are positive, they are all the same size. So this family, so this classification results is due to Ernst Heinze in 1973. That's why these spaces are called Heinze spaces and the Heinze groups. Right. And there are non-Archimedean versions of this. Anytime you can produce a semi-direct product of a locally compact group, nilpotent group, by a group which acts in a contracting manner, where contracting is not very demanding. You merely ask that any element by the group S can be carried in a fixed compact set. So that's not very tricky. So there are many examples, non-Archimedean examples, as in the real case. So this is what we will call a groups, Heinze groups. So by construction, these groups are hyperbolic. And now here comes a classification theorem. So in this family, either connected Lie groups or algebraic groups over local fields, in characteristic zero, we can tell exactly which are hyperbolic. They are exactly either the Heinz groups or the rank 1 groups. On these easy examples, nothing else. So this comes out of a result which is a computation of Lp-cohomology for in these classes, connected Lie groups or algebraic groups over local fields of characteristic 0. And here is the result. It's a trichotomy, 3 exclusive cases. First, the amenable case, where so then the torsion is non-zero and the reduced part of cohomology is 0. So in some sense, okay. The second class is our favorite examples, these Heinz or rank 1 groups, for which torsion vanishes and reduced cohomology does not vanish for P large enough, and as is expected for hyperbolic groups. And the third class is all others, for which Lp cohomology is 0 always for all P, because so now the classification of hyperbolic groups readily follows, since hyperbolic groups, they have some reduced Lp cohomology for some P, so they have to fall in the second family. So now I will explain the proof of this theorem in the connected Lie case. The other case being rather similar, but harder to explain, formulate. Whereas for the Lie case, I already have the definitions of it at hand. So the point is simply have a connected Lie group, try to compute its Lp cohomology. So let's do this. Before this, sorry, I could explain how torsion enters the picture. I'm sorry. I forgot this step, which is completely independent. So this has to do with isoperimetry. So you remember that vanishing of torsion exactly means that closed forms have a primitive which is controlled in a binorm. So in degree 1, since the primitive is unique up to an additive constant, this boils down to a Sobolev inequality. And now it's not hard to see that Sobolev inequality with some P, exponent P, is equivalent to, if you have it for P equals 1, you have it for all P and conversely. So passing from P equals 1 to other values of P is simply applying Sobolev inequality to U to the P and applying Hölder's inequality. So it's straightforward. With the same with control of constants. The converse requires bounded geometry. It requires more or less discretizing the inequality, and then seeing that it can suffice to prove it for functions which take only values 0 and 1, and then taking P's power simply doesn't change anything to them. But it's a trick. Now the fact that the L1 Sobolev inequality is equivalent to linear isoperimetric inequality has been known for decades, at least maybe not a century. So that's a manifestation of Poincaré duality in the world of forms and currents. Right. So we see that torsion non-zero group equivalent to linear isoperimetric inequality. And now we know the isoperimetric behavior of Lie groups quite well now, but the case whether linear or non or less than linear, this was known already 30 years ago. So exactly amenable unimodular groups. So this explains the first category in the classification theorem. So now I can go to the Lie group case more thoroughly. So I'll do a few lines of computation with differential forms, if you don't mind. So let me remind you of a step in the basic course in Durham cohomology. One of the first things you need to prove is the homotopy invariance of Durham cohomology. To prove that if two maps are homotopic, they induce the same thing, the same map in cohomology. It's a smoothly homotopic. And then the lemma, which you need, says that when so two smoothly homotopic maps means to a space means a map to the product manifolds times interval. And your two maps are obtained by we could put it R, it doesn't cost anything. And you have the two injunctions of M in R times M as 0 times M and 1 times M. And the key thing is to prove that these two maps induce the same map in Durham cohomology. If you do this, then it's proved homotopy invariance, smooth homotopy invariance, and then bicentric homotopy invariance. So how is this done in textbooks on Durham cohomology? One uses the flow of translations along the real line factor, right? And one shows that this map induces the identity in cohomology. So how does this work? So this flow is generated by the vector d over dt. And then so imagine I have a form alpha, and I pull it back by this flow, phi t star alpha. It's a one-parameter family, smooth one-parameter family of forms. What is its differential? So I have a formula in my pocket that does this. It's the Lie derivative which enters. And now Cartan's formula expresses the Lie derivative of differential forms in terms of the exterior differential on one hand, and the inner multiplication with the generating vector field psi. It's the formula d xi plus xi d. So now the d commutes with pulled back by diffeomorphisms, and so we start getting a formula that looks like d of something plus something of d, which is a good sign. We're in good shape. So now let's take this expression phi t star xi alpha and integrate with respect to t. So, and when you plug this in the formula, after all, you're integrating a derivative, a time derivative. And so the conclusion is that phi t star alpha minus alpha is given by such integrals. So it takes the form dkt plus ktd, and so clearly induces the identity on cohomology. Now, let's simply use this formula in a different setting, not for a product manifold, but for a warped product manifold, a Lie group and a left invariant vector field. So the picture you should have in mind is this one, where the vector field is the Boltzmann vector field. Unit vector field whose orbits are the basics emanating from one point at infinity. So if psi is left invariant, its length is constant. But how does it behave? How does the flow of phi act on zero forms and one forms? On zero forms, it's easy. It's just a question of volume, and it depends on the divergence of the vector field. And here, in fact, if alpha is a one form, xi alpha is a function, it's zero form, so I'm simply pulling back zero forms. So only the divergence of xi will play a role. If divergence is non-zero, then Lp norms of zero forms will be contracted exponentially. And so the integral there, I can push it up to t equals plus infinity. And so these operators converge to bounded operators on Lp. So this shows that this form phi t star alpha converges to some limit which I denote by alpha infinity, and which can be viewed either as which is now a form on the whole group, but which is invariant under the one parameter group generated by psi. So, and the formula furthermore shows that the cohomology class of alpha is zero if and only if this limiting form is zero. So it's clear that if the limit here is zero, then alpha will be exact, but the converse is easy from even easier. So in this way, we have produced a homotopy where we, in fact, this operator which maps alpha to alpha infinity is non-homotopic, is homotopic to identity, but it maps to a different complex of differential forms. Forms which are invariant under this flow, but we've lost some regularity. They are not in Lp anymore, but they are at least in L minus 1p. So this is a Kunus formula. If we are dealing with a direct product, then this would be a Kunus formula. This minus 1p will not be completely harmless. But the picture is rather like this, like a twisted product. Metrically, topologically, it's a product, but metrically, it's not. And so we get this weird L minus 1p cohomology to compute. It turns out that in degree 1, one can go and continue a long way up to a full answer. The same method works in higher dimensions, but the calculations are not as complete. Sometime I will tell you a few examples of results of such calculations. You see, it's kind of a twisted, warped Kunos formula that we're playing with here. And up to now, we've not used any Lie group theory, except the fact that this vector field has constant divergence because it's less invariant. So now there will be a little bit of Lie groups and Lie algebras. So first, the trick. Let's reduce to a smaller class of groups, triangular groups, that is subgroups of triangular matrices. So it's a fact that every connected Lie group is quasi-isometric to such a group. So this makes our life easier. Now the resulting group can be either unimodular or not. So if it's unimodular, then it's solvable unimodular, it's amenable. And now, here comes Teixeira, who proved that the reduced cohomology of such groups has to vanish. So he uses the Fellner property in a strengthened manner. So not only do we have Fellner sets in such groups, but these Fellner sets have a diameter which is linear in the 1/n here. He called this controlled Fellner sets. So presumably not all amenable groups admit such controlled Fellner sets, but many of them do. In particular, all these amenable Lie groups do. And using this control on Fellner sets, Teixeira is able to show that cocycles of mixing representations have to tend to zero, have to be sublinear. And so this implies, and now sublinear growth for a cocycle implies that this cocycle is in the closure of coboundaries. So that's a nice idea by Teixeira. Now, the non-unimodular case, then I can pick a left invariant vector field whose divergence is non-zero and use the previous warped Kunos formula. So, what happens? So imagine you have such a form and obtained by some limiting procedure, so it's not very regular, but it's invariant under the flow of Xi, and it must be invariant under other flows of all other vector fields in the Lie algebra, which are contracted by Xi, and even weakly contracted. Because otherwise there would be exponential expansion of norms of that form, and it's incompatible with belonging to L-1p. So we see that the one form that was initially invariant under only one flow suddenly is invariant under plenty of other flows, all those which are weakly contracted. And so this implies as soon as you have a second invariance, you're done, because we are dealing with objects which have an integral norm which is finite. How can you have some integral norm which is finite and at the same time being invariant under translations? So the only case left is when our initial vector field did indeed contract strictly all other left-inline vector fields. That's precisely the Heinze case. So, and so we are done. So to perform this calculation, so we've used the same idea that was valid in hyperbolic groups, survives at least for Lie groups, but not quite with the same meaning. So this alpha infinity cannot be interpreted as a form living on some boundary, as it can be. It is so in the hyperbolic case. This interpretation fails in the general case. And so what remains is the Kuhn's character. So, and secretly here I've used this interpretation of Lp-cohomology of a group as P-cohomology of the group with respect to a certain Lp representation. I think it's time to stop for today. I don't know whether. Oh no! I should instead give you problems to solve for this.
No, instead.